here, and we are doing a hands-on session on DBSCAN today. So DBSCAN is a clustering algorithm, and it is a density-based clustering algorithm. So one of the fundamental question is that k-means, which is such a popular and simple algorithm, are there some cases where DBSCAN performs better than them? So this is the question, this is the quest that we are going to pursue in this particular session. So what are some of the questions? The questions are the parameters of DBSCAN, how DBSCAN does with respect to noise, okay, to values which are outliers with respect to k-means. We will also look at k-distance plot, how it can be used to find one of the parameters, critical parameters of DBSCAN. We look at classic data sets like moons and circles and how DBSCAN works on them. Okay, so let's get started. All right, so just a quick revise. So there are two very important parameters of DBSCAN. Okay, so we talked about density, right? So for density, we need to attach a concept of area. Okay, so if this is a point and I am trying to find the density of this point, what I am going to do is I am going to draw a circle around this. What will be the radius? The radius is called as epsilon. So this is one of the critical parameters of the algorithm. All right. And as I said that there will be points which will be classified as core, border and noise points. Let's just focus on the definition of core points. Okay. So once I draw a circle with this epsilon radius, what I'm going to do is I'm going to count how many number of observations are falling between this. Okay. So if it is beyond a threshold, so if it is equal to or more than that threshold, then we call this as a core point. And when we do the calculation, we calculate or count this point as well. Okay, so this threshold is called as mean points. So epsilon and mean points are the most important parameters of this algorithm. Now we are also going to do our comparison with k-medoids. As we know, k-medoids is also very good in handling outliers. As k-medoid is not available in sklearn, we have installed sklearn extra over here. Okay, so let's look at some of the questions now. The questions are, what are some of the important parameters? So one of the important parameters is epsilon, as we discussed. Second is mean points, which we have also discussed. Now, when we are trying to calculate distance, of course, we will have to use a distance measure. So here we are going to use the Euclidean distance measure. Okay, and some cases you may get also the distance matrix as an input, right? So if the distance matrix you want to give as an input instead of the data matrix, then you will mention the metric to be pre-computed, and as it is a distance matrix, it must be a square matrix. Okay, and what are the output it produces? So one of the important output that it produces is called as labels. Okay, so labels is basically will give you the different cluster labels. Okay, and the dimension, this is an array, and the dimension of the array is going to be number of samples present. Okay, now let's go ahead and see question 2. So what we are going to do is we are going to introduce some outlier points and see how DBSCAN performs with respect to k-means and k-medoids. Okay, so what we are going to do is we are going to do our usual imports. We'll import DBSCAN, we'll import NumPy, we'll import plot, we'll import k-means, k-medoids will be from sklearn extra. Now what we are going to do is we are going to define a list, and then we are going to vectorize it such that if we run vectorizer on some list, what will happen is it will look at how many elements are there in the vector, and then it will pick that many colors. Okay, so this will use actually to color different clusters in different way. Okay, so let's run this. Okay, now let's create a database or data set where you have just 1 2 3 4 5 6 7 observations. Okay, and if you see, only one of the observation is outside of this range. Okay, so let's create it and also do a scatter plot. Okay, now if we look at the scatter plot, see, this is what we were expecting, and Now, without going into any complex algorithm, you might agree that this is one of the clusters and this is also one of the clusters. So there are essentially two clusters and this point is an outlier. Okay, so this is what probably your intuition will be. Okay, next we have just defined a function called as class plot, which essentially plots the different clustering results of DBSCAN, k-means and k-medoid. Okay, so let me run this and now let's try fitting DBSCAN, k-means and k-medoid. Okay, so let me run this quickly. Okay, so DBSCAN, as I said, gives an output like clustering dot labels. Okay, so if you try to look at what is there in Y, that will be interesting to note actually. Okay, so you have something like 0, 0, 0, 1, 1, 1 and -1. So do you know what is -1? So every cluster that are around core points, they will have same cluster level, if you remember. The noise points are identified by -1. Okay. So I think we have diverged already a lot, but still let's do one thing. Let's just plot this, okay, and see how how this algorithm, three algorithms compare vis-a-vis each other. Okay. So you remember the 7 points, right? So if you look at DBSCAN has identified this to be three to be one of the cluster, this tree to be another cluster, and this one is a noise point. If you look at k-means, the cluster is completely disrupted because of this outlier point. So it has now told that these are actually clusters. So original points are not clustered at all. The outlier has disrupted it so much. Okay. However, your k-medoid creates two cluster and it puts this inside the second cluster. Okay, so there is an improvement in k-medoids from k-means. However, DBSCAN gives you the most intuitive result. Okay, all right. Uh, Now let's go ahead and see how we can find the k distance using your epsilon. So here the idea is, okay, so we are going to generate a data set for here. So let's create a data set. So we are going to use a function called as make blobs. So make blobs actually can create different Gaussian distributions. Okay, different Gaussian distributions. So here we are saying we are going to create three Gaussian distributions. All of them has same standard deviation, and we are using a random state just for reproducibility of the result, as you know. Okay, so now when we have done the scatter plot, you see that these are the different clusters that you have got. Now the tricky thing is your standard deviation. So if you increase your standard deviation little bit, let's make it 0.8, and if you make it 0.8, see, you see that they are converging closer, right? So the lesser the standard deviation, more compact the clusters will be. So let's go back to our original 0.6. Okay, all right, and these are well separated clusters. Okay, so now what we are going to do is we are going to use nearest neighbors from sklearn, and we are going to run it with neighbors equal to 10. Okay, so I will explain you further. So let's just run this quickly. Yeah, so now what is happening is we will get a distance metric over here. So let's run the distance metric. So what is happening is, that each of the rows, if you see, has, so this is a 2D matrix, okay? So it has columns like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So let me reduce it little bit. Let me make it 3 first. Okay, so if I make it 3, yeah, so it is run now. Let's run this. Yeah, now it is more clear. So this inner dimension has three elements. Which are these three elements? These are distance with the three closest neighbors. So the first closest neighbor is itself, so it will always be 0, and then you have the next two neighbors. Okay, so this is how you have to interpret the distances. Let me change it back to 10. Okay, And basically what k-distance plot does is actually, it takes a parameter like which neighbor you are going to look at. So let's say it is the fourth or third neighbor. So what you do is you plot, you actually get this column out, right? Track this array. Then you sort it and plot, okay? So wherever you see a sharp rise in this kth neighbor distance, that means that there is a big change, and probably you are transitioning from the core points to the border point and the noise points, okay? So that value you can take as an epsilon, okay? So let's look at distances. Yes, so now it has again 10 elements. Let's go ahead, and as I said, we are going to sort, and then we are going to look at the distance of the fourth neighbor. So if you remember the thumb rule, then minimum points that we are going to take is 2 into number of features. So we have 2 features, so it will be 2 into 2 or 4, okay? And next what we do is we are also going to look at the distance with the 10th neighbor, okay? And then we are going to simply plot this, okay? So if we plot, the points, or the graphs shows quite similar pattern, right? However, the change is much drastic when we have looked at the fourth neighbor. So that is the reason probably the uh, fourth neighbor will be more suitable to look at or find the EPS. Now, if you look at the sharp rise, probably if you go from maybe 0.3 or somewhere, so from there is a sharp rise that is starting. Then your EPS value you can keep between maybe 0.2 to 0.3, okay, or maybe 0.4. So let's run this clustering algorithm with EPS equal to 0.4 and mean samples equal to 4. Okay, let's look at Y now. Okay, so if you look at, the cluster levels are 0, 1, 2, okay, 0, 1, 2, and then there is also -1. So -1 are the noise point. But before that, let us see something. So if I make EPS to be a very, very high value, let me make it as 10. Can you tell me what will happen? So all of this will come to same cluster, isn't it? So let's run this and see what happens. Okay. So if you see, all of them are now 0, right? And if I make it very, very small, let's say I make it 0.001, okay, what will happen? Can you tell me? So probably each point now will be in its own cluster. Okay, let's run and see if that is what is happening. Okay, so actually, as I have given this mean samples as 4, all have been created as noise points, right? So everyone is -1. What should be the mean samples value if I want everyone to be core? I should probably change it to 1. So let's run and see what happens. All right, so let's run this. Yes. So now if you see, you have so many clusters that has come up, right? So the number of observations that are there, that many clusters has come up. So there are 300 observations. So that's why you have got 300 clusters. So let's go back and change to 0.4 and mean samples equal to 4. Okay, so this is how you can test around EPS and see the effect of EPS and mean samples both. Okay, all right, so let's run it back. Okay, now uh, let's once plot this and see whether it has correctly identified those points. So how the points look like, let's go back and see. Yeah, so this is how the clusters were. Now let's see if this can correctly identify the clusters. Okay, so let me run this one. Yeah, so just see that it has very nicely carved out the 3 clusters in different colors, and also which are somewhere in between or far from the clusters, it has identified them as noise points. Okay, so it actually beautifully works in such a well separated clusters. However, your criticism can be that this should work well for k-means as well, isn't it? Okay, so let's look at some of the cases, classic cases. So one particular data set is called as make moons. Okay, so which are like concentric half moons. So if I use this make moons function and create a sample of 150 with a noise value and I give you the scatter plot, probably it will be much more clear to you. So this is how the data set looks like. Okay, so this will be a test for k-means and k-medoid if they can do well, or can DBSCAN be better than these two algorithms. So let's run our algorithms from each one of them. So if you remember, these are already initialized. Okay, so we are just going to run this k-means predicted. We are going to look at the clustering levels from DBSCAN, and we are going to also apply y k-med. So basically this will fit the data on this make moons data set. Okay, all the three clustering algorithms. So you can take a look at y, how it looks like. So the values are 0 and 1. So DBSCAN also identified this as two clusters. Now let's run, let's see how this has been marked. So if you look at DBSCAN, it has done an excellent job. It has correctly identified these two clusters. However, if you look at k-means, k-means always tries to find some kind of a regular shape, right? So it has missed the patterns, and however, it has probably done little bit better than k-medoids, or they are equivalent. However, both of them has missed out that there is a big density gap from this cluster and this cluster. Okay, so that's why actually DBSCAN emerges as a very good clustering algorithm. Okay, so let's look at another one. So this is also a very classic data set where you have concentric circles as the data. So let's look at the data and it will be much more clear to us. Yeah, so this is how the data looks like, in case of make moons, make circles. And now we will do the same exercise. We are going to fit all of k-means and DBSCAN and k-medoid, right? And what we are going to do is we are going to just compare them through a scatter plot. So done. All the algorithms are fit on this particular on this particular data set, and the labels are predicted. Okay. So what is remaining is now just looking at the cluster plot. Okay. So these are DBSCAN levels 0 and 1. So can make us little bit optimistic. Let's now run this cluster plot and see how the results are. Okay. So look at this, right? DBSCAN has again have correctly identified this cluster. So of course you have by now understood that whichever points are in the same cluster, they are with the same color, and if they are not in the same cluster, they will have different color. So you can see that it is completely, DBSCAN has completely swamped k-means and k-medoid, has correctly identified these two concentric circles as different clusters. Okay. So, in today's lectures, through several demonstrations, we tried to explain where DBSCAN needs to be used. Hopefully, you have enjoyed it, and please give your comments, questions, and we'll try to get back to each one of them to the best of our abilities. Thank you so much. Please like, comment, and subscribe. Thank you.